Good evening, students. We are discussing syntax analysis. In that, we have discussed regarding SDT. After that, introduced just S attribute definition and L attribute definition. I will again discuss about S attribute definition and L attribute definition. After that, we will move to the translation scheme. So just we will see some more things about S attributed definition and L attributed definition. So 1 second. So SDT can be or can have two kind of attributes. One is S attributed definition. Another one is L attributed definition. S attributed definition and L attributed definition. Sir, when we call the SDT as S attributed definition, or when we call the SDT as L attributed definition. Yes. Suppose if SDT uses only synthesized attributes, then we can call the type of attributed definition is S attributed definition. Suppose all the attributes are synthesized attributes, then we can call that kind of SDT as S attributed definition. Suppose if it uses or SDT uses synthesized attributes plus inherited attributes, synthesized attributes and inherited attributes, then we can call that one as L attributed definition. L attributed definition. We know about synthesized attribute and inherited attribute. Suppose if any attribute is defined, with the help of its children, then we can call that one as synthesized attributes. Suppose if any attribute is defined with the help of children, then we can call that one as synthesized attribute. Coming to the inherited attribute, it is defined or it is computed with the help of parent or left sibling. So that kind of computed attributes are called as inherited attributes. In the SDT, we have two kind of attributes. One is S attributed definition, another one is L attributed definition. If any definition or attributed definition having only synthesized attributes, then we can call that one as S attributed definition. Suppose if any attributed definition having synthesized attributes as well as inherited attributes, then we can call that one as L attributed definition. These are the two different kind of definitions are there, sir. From this, we'll get the question as they will provide some SDT and they ask which type of attributed definition it is. Suppose if you see here, some SDT is given like this. Sorry. TL. T derives int. L derives L comma ID. L derives ID. So this is the CFG. We know about it. By adding semantic rules, we'll get we'll get SDT. SDT is nothing but CFG plus semantic rules. The semantic rule for this is L dot type equals to T dot type. And here T dot type equals to int. Here L1 dot type equals to L dot type and so we are having two here. L derives L comma ID. So along with this, it is having one more thing, sir. That is, we need to add type. So here ID dot name comma L dot type. So here we need to add ID to the L, sir. So for that purpose, we are having one function that is nothing but add type. Add type is the function. This is the predefined function, sir. So we use this. So here also the same. Add type of ID dot name. ID dot name equals to ID dot name comma L dot type. ID dot name equals to L dot type. These two are functions. These two are functions. So these two are not considered as attributes. Inherited attribute or synthesized attribute, we can't decide regarding these two, sir. So we need to consider about these three for this one, and this one. So what type of attribute it is? Is it a synthesized attribute or inherited attribute? Is it a synthesized attribute or inherited attribute? Synthesized attribute means suppose if we inherit the properties from children, if we inherit the properties, then we can call that one as synthesized. But here L dot type is getting the properties from T dot type. This is nothing but T is the left sibling. T is the left sibling. So I already informed. So here, if it takes the properties or if it is computed from left sibling or parent, we can call that one as inherited attribute. That's why this is the inherited attribute. This is inherited attribute. And coming to the next one, T dot type equals to int. Here int is the child, so T is getting or T is defining or computing from its child. That's why we can call it as synthesized attribute. And coming to here, L is computed from its child, and as well as there is some definition here, That's why we can call this one as, by using this add type of ID name is added to the L dot type. This ID is adding to this one, sir. So that's why we can call this one as inherited. So finally, we can say that already synthesized is there and inherited is there. If any SDT having synthesized and inherited, we can say that grammar that SDT is syntax directed translation is called as L type attributed definition. So we'll get the questions as which kind of attributed definition it is. So for that purpose, they may give some grammar or some SDT. From this SDT, we need to check, is it having inherited attribute or is it having synthesized attribute? From that, we need to say that is L type attributed definition or S type attributed definition or none of the above or both, like that. So here in the given question, the options are, first option is yes, second option is L, third option is A and B, and fourth option is none. So here in the given SDT, there are inherited attributes as well as synthesized attributes. If any grammar having synthesized and inherited attributes, we can call that one as L attributed definition. L attributed definition. So answer is L attributed definition, sir. So here the answer is L attributed definition. Like that, we'll see one more question, sir. Here, suppose S is deriving AC, S derives A, B, M, C, C derives 4, M derives epsilon, A derives epsilon, B derives epsilon, B derives epsilon. And here the rules are C dot X equals to A dot X and M dot X equals to A dot X plus B dot X. These are the rules, sir. These are the rules. And one more rule is C dot X is equals to 4. C dot X is equals to 4. For epsilon productions, they don't give any kind of rules, sir. So here, this is CFG and this is semantic rules. So finally, we can say that this is the given SDT. Finally, we can say that this is the given SDT. For this given SDT, he is asking what type of attributed definition, it is. So for that purpose, the options given are capital S, that means S type attributed definition, and second one is L type attributed definition, and C both, and D is none. So to choose the answer, first of all, we need to check the grammar or the given SDT having which kind of attributes, synthesized attributes or inherited attributes. So coming to here, A is the left hand side non-terminal and C is the right hand side non-terminal. It is defining from the left sibling. Suppose if any rule or non-terminal is computed from its left sibling, we can say that that is inherited attributes. And here also M is deriving or computing from its left siblings A and B. By computing A and B, so we are defining M. So for that purpose, it is also inherited attribute. Coming to here, C is deriving from its child. So we can give it as synthesized attribute. So if any SDT having both synthesized and inherited, we can call that one as L attribute. We can call that one as L attribute. So you may get the questions in GATE from S attributes and or S type attribute definition and L type attribute definition like this. So they will provide or they will give some SDT. So in that SDT, you may have some grammar as well as some semantic rules. From these two things, we need to first of all check what kind of attributed grammar it is, what type of attributed grammar it is. So suppose if it is inherited attributed, so are synthesized attributes. Suppose if it is inherited attributes, so inherited and synthesized, we can call that one as L type definition. And suppose if it is only having synthesized attributes, we can say that that is S type attributes. So that is the thing, sir. Sometimes you may get the questions on this area also, sir. On this area also, L attributes and S type attributed definition. So this is the thing, sir, from SDT. So next we will move to the translation schemes. Suppose before moving to the translation scheme, if you are having doubts regarding S attribute or L attribute or inherited attribute or synthesized attribute, you can ask, sir. SDT can be represented in two ways: S attributed definition or L attributed definition. S attributed definition means, suppose if it is having only synthesized attributes, suppose synthesized attributes and inherited attributes both are having, then we can call that one as L type of attributes. Synthesized attribute means that attributes are computed or that is defined by using its children. So from children, if it is computed, then we can call that one as synthesized attribute. Suppose from left sibling or parent, if we compute that one, we can call that one as inherited attributes. Then we can call that one as inherited attribute. So from these, if you are having any doubts regarding, will clear, sir, you please ask. Okay. So the next concept is translation scheme. The next concept from semantic analysis is translation scheme. So translation scheme means, suppose if you take any SDT, in which in that SDT the semantic rules may present middle of the production. Semantic rules may present in the middle of the production. Sir, what is production? Production is nothing but if you take any grammar symbol or if you take any grammar, in that you may see like this. S derives AB, A derives small a, B derives small b or epsilon like. So we can call this one as a production and this one as a production and this one as a production. Collection of productions is nothing but grammar. Collection of productions is nothing but grammar, sir. Collection of productions is nothing but grammar, sir. In SDT, we are having two things. One is grammar, that means CFG, plus along with that, the semantic rules are there. If the semantic rules are placed, are present in the middle of the production, up to now, the semantic rules are like this. S derives AB, a dot type, a dot type, or else, sorry, okay, sir. S dot type equals to a dot type plus b dot type, like so. After completion of the production, we are having semantic rules till now, but now if you see, the productions are look like this. S derives tr, r derives plus t, print plus r slash epsilon. So this is the production. In this production, we are having the semantic rule. We are having the semantic rule in the middle of the production. In the middle of the production. Suppose if any production in Sdt, the semantic rules may present, semantic rules may present in the middle of the production. So that kind of productions is called as translation scheme. That kind of productions is called as translation scheme. Translation scheme is nothing but Sdt. Translation scheme is nothing but Sdt. In that Sdt, semantic rules may present in the middle of the production. In the middle of the production, like this. In the middle of the production, like this. Or t derives num print num dot value, like this, like this. Here productions are middle of the production may be the semantic rule. If any production having the semantic rule in the middle of the production, or any grammar having the semantic rule in the middle of the production, that is called as translation scheme. That is called as translation scheme. That is called as translation scheme. So Sdt and translation scheme both are same, sir. Sdt translation scheme is also called as Sdt. Translation scheme is nothing but Sdt, or translation scheme is also called as Sdt. But in that Sdt, the productions having the semantic rules in the middle of the production. Semantic productions having semantic rules at the middle. So the type of process or the type of situation is called as translation scheme. The type of situation or that kind of process is called as translation scheme. So translation scheme is nothing but Sdt, but the production's middle we may have the semantic rules. So how to construct a translation scheme from the given Sdt, we will see, sir. How to construct the translation scheme from the given Sdt, we will see, sir. So first thing is construction of translation scheme. Construction of translation scheme. So here the rules are, the first one is all synthesized rules. All synthesized attribute rules placed of all synthesized attribute rules placed of rightmost end of grammar production. And second rule is all inherited attribute rules, all inherited attribute rules can be placed at middle of grammar production in a proper position. Middle of the grammar production in the proper position. That means, suppose, sir, can we write this print between plus and t? No, sir. So that is not the proper. Sir, can we write this after r, sir? So that is not a proper. So it has to fulfill the thing what we have processed with Sdt. So Sdt and the translation scheme both should accept or both should provide the same things, but the representation is different. Sir. The representation of Sdt and translation scheme is different. That's it. But the work of translation scheme and the work of Sdt both are same, sir. Same. That's why we need to place the semantic rules at the middle of the production and in the proper position. We should not place at any other position, sir, other than the proper position. So what he is mentioning is all the synthesized attribute rules placed rightmost end of the grammar production. Suppose if the rule is produced or the rule is placed at the end, that kind of attribute is a synthesized attribute. Or suppose if it is a synthesized attribute, we have to place the rule at the end. Suppose if it is the inherited attribute, then we need to place the semantic rule in the middle of the production. So suppose if we see one example, there is a grammar or there is a Sdt like this: AB, A derives, BC, and B derives small b, capital C derives small d. And the rules are S dot x equals to A dot x. S dot x is equals to A dot x. C dot y equals to B dot y. So this is the question given, sir. So suppose if you see here, I can call this one as Sdt. Sir, why you are calling this one as Sdt? Because if any context-free grammar along with semantic rules, I can call that one as Sdt. That's why I am calling this one as Sdt. For this Sdt, now I need to construct translation scheme. For this, I need to construct the translation scheme. Suppose if we see before constructing translation scheme, we need to see, is it a synthesized attribute or is it a inherited attribute? Suppose if it is a synthesized attribute, the rule must place at the right hand side of the production or the rightmost end of the grammar production. So suppose if it is the inherited attribute rule, then we can place middle of the production. So that's why first of all we need to check what kind of attribute it is. Suppose first we see this. S is computing from A. S is computing from A. Here, A is the child of S. A is the child of S. A is the child of S. That's why we can say that this is synthesized. This is synthesized attribute. For synthesized attribute, we need to write at the rightmost end of the production. So that's why we need to write S dot X equals to A dot X. A dot X. So, and now if it is inherited attribute, if it is inherited attribute, we need to place in the middle of the production, or we can place middle of the production based on the proper position, Now, if we see second one, C is deriving from its left sibling. Here, C is computing from B. C is computing from B. B is the left sibling of C. B is the left sibling of C. That's why it is, suppose if any grammar production symbol is computing from its parent or its left hand side sibling or left sibling, we can call that one as inherited attribute. We can call that one as inherited attribute. So now it is inherited attribute. Suppose if it is an inherited attribute, the rule can be placed. In the middle of the grammar. Okay, sir. In the middle of the grammar, we can place. At what place we need to insert? At what place we need to insert? Because here, if you see, A derives BC is there, sir. A derives BC is there. Right hand side of the production, we need to insert. Sir, after B and before C, can I insert? We will see it, sir. We will see it. Some rule is there. The rule is, if any translation scheme, if it is inherited only, we use this one, sir. If it is inherited attribute only, we use this one, sir. If any translation scheme is inherited attribute, the semantic rule is placed. The semantic rule is placed before the non-terminal, before that non-terminal. Sir, which non-terminal, sir? If you see here the thing is, the computation is based on the C, sir. We are considering here it is C. So here C is computing from B. So our consideration is C. That's why before C we need to insert. So A derives B, and the rule is C dot Y equals to B dot Y. C dot Y is equals to B dot Y. This is the rule. This rule is inserted middle of the production. Then we can call that one as, then that one is called as translation scheme. So this is the translation scheme. So B derives B and C derives D. Sir, we don't have rules for these two, sir. So no need, sir. For sometimes they may give rules for every symbol and for some, or sorry, for every production, and sometimes they may give only for the some productions. For those productions, we need to write. For those productions, we need to write or we need to translate, sir. We need to translate. So this is the way. This is the way of construction of translation scheme. This is the way of construction of translation scheme, sir. For the given Sdt, suppose if any Sdt is given, then we can construct the translation scheme for that. Construct the translation scheme for that. Suppose if it is a synthesized attribute, we write the rule at the rightmost end of the production. That is same. So Sdt is same and synthesized is same. Suppose if it is inherited, in that case only, we need to insert in the middle of the production. For that purpose, we need to check the rule. If it is the inherited attribute, the rule is placed, or the semantic rule is placed before that non-terminal. That is nothing but computed. Non-terminal. Before the computed non-terminal, we need to place the semantic rule. That is the proper position. We should not place at any position. We should place the before the non-terminal or before the computed non-terminal. We can call that position as proper position. So this is the way for the construction of translation scheme for the given Sdt. So these are the rules, sir. If it is the synthesized attribute rule, so directly we can write it. Suppose if it is inherited only, we need to rewrite it, or we need to insert in the middle of the production. So that is the thing, sir. Next one is how to evaluate translation scheme, or how to evaluate semantic rules from translation scheme. I already told you Sdt and translation scheme both are same, but this is the another format of Sdt. Translation scheme is the another format of Sdt. So with the Sdt, we evaluated the rules. In the same manner, for the given translation scheme, we need to evaluate. So for that purpose, we are having some rules. Again, we are having some rules. So we will see. First of all, we need to construct the parse tree. For the given string with the given grammar. And second thing is attach semantic rules. To the parse tree. By considering them as grammar symbols. And third one is perform DFS traversal from left to right. Sir, for evolution of evolution of translation scheme, we need to do these three steps. These three steps. The first step is need to construct the parse tree. Need to construct the parse tree. And second one is need to attach the semantic rules to that parse tree by considering the grammar symbols. And finally, we need to perform the DFS traversal for the from left to right side. So we will see one example. With that example, you will get better knowledge how to evaluate the given translation scheme like that, sir. So suppose if you take translation scheme, S derives TR, R derives plus T, print plus R slash epsilon. This R is also belongs to this one only, sir. And slash epsilon. So that means R is deriving this one as well as R is deriving epsilon. So that is the meaning of this one, sir. This one. So right. Yes. See this. T derives num print num dot val. So this is the translation scheme given, sir. And in the question he mentioned here, num is a token. Num is a token that represents an integer. And num dot value represents the corresponding integer value. For input string, 9 plus 5 plus 2. This translation will print option A, option B, option C, option D. 9 plus 5 plus 2. 9, 5 plus 2 plus. Option C, 9, 5, 2 plus. Option D, plus 9, 5, 2. So these are the given, sir. This is the given question, sir. This is the previously asked question also, sir. Previously gate asked question also. So in the translation scheme, the grammar is given, the productions are given, and the question also some rules are mentioned. Num is the token that represents integer, just integer, not an integer value. It is an integer. It mentioned it is an integer. And num dot value is there that represents integer value. For this input, with this translation scheme, which one of the output is correct, or which one of the evolution is Correct, sir. So this is the question. So in the question, they will give some grammar as well as some input string, some grammar and some input string. Along with that, they may give some rules. Num is the integer and num dot value is the integer value, like that. We need to follow those. We need to follow all those. So we'll see. So here 9 plus 5 plus 2 is the given string. We need to accept this string. We need to accept this string. For that purpose, he has given the grammar as S derives TR and R derives plus T print plus R slash epsilon, and T derives num print num dot value. But this is, so we are having some rules for evaluation. We are having some rules. The rules are, first we need to construct the parse tree. First we need to construct the parse tree for the given string. For the given strings. First we need to construct the parse tree for the given string. Suppose if you construct the parse tree, S is deriving TR. S is deriving TR. So, and T is deriving num, comma, num, and print num dot value. Print num dot value. This is num. That is nothing but this represents some integer. This represents some integer, but it does not represent integer value. And after that, R is representing the, right, like this. Wait. S derives T R, sir, from T num print num dot value. Print num dot value is there. Coming to the R, there are two things. One is this one, another one is epsilon. After printing 9, I need plus. So that's why in place of R, I am taking plus T print plus R in place of epsilon. So other than epsilon, I am considering plus T print plus something. I am considering this one, not this one, because I need plus after the printing value 9. So that's why I can write it as plus and T, after that print plus, after that again R. So now if I expand it, here 9 value will print, and this T needs to print 5. This T needs to print 5. That's why I am expanding this one as, or else there is no other way. Suppose if T is there, so only one option is there. That is num and print num and print num value. So here 9 printed and here 5 also completed. So again I want one more plus and 2. If I take epsilon in place of r, I can't. So that's why I am again taking plus t print plus r. So for r plus t print plus and r sir. So plus is the terminal, we can't expand it. T can be expanded as num print num dot value, print num dot value. Here 2 is also completed. So 9 completed, 5 completed, sorry, here 2 completed. So that's why this r can be replaced with epsilon. This r can be replaced with epsilon. This r can be replaced with epsilon. So this is the parse tree. This is the parse tree. This is the parse tree. Now he mentioned after construction of the parse tree, what we need to do? Sir, attach the semantic rules to that parse tree. So here the semantic rules are print dot value, which value it needs to print? 9, because the first value is 9. And which value here? This is the print, is the semantic rule 5. Here it is 2. So semantic rules also added for the parse tree as a grammar symbols, Now we need to do is DFS from left to right. So this is the thing we need to do. So DFS means we need to start at root. I move to the plus. Is plus having left child? Yes, there is a left child. After completion of left child, I need to move to the right child of plus, because there is no left child and there is no right child for num. I need to move to the again to the right child, or else I can write it as directly. I can move to the sibling. What is the sibling here? Print value. What is the value here? It will print. What is the value? It will print 9, sir. Sir, why you are printing? Because the left value completed, right value completed. For plus, left value completed, right value completed. So that's why I am performing this action. The action is, or the rule is, print the num value. Num value means, here he mentioned, num value means integer value. So that integer value I am printing, or I am taking. So after completion of left subtree, I need to move to the sibling of right child. So for plus, the sibling is r, sir. For plus, the sibling is r. From that r, the leftmost is plus. Is there any action need to perform here? No, sir. Not mentioned. Print plus is not mentioned. So that's why there is no left and there is no right. Next, I move to the t, not to r, sir. So I need to finish all this level, all the elements in this level. That's why I need to move to the t. Coming to the t, there is a left child and there is a right child. Suppose if I move to the left, so I can't do anything here. So then what is the right child of or sibling of num? So parent. So that is print num value. That is 5, sir. So just print 5. So this is completed. After completion of this one, it needs to move to the sibling. So right sibling. What is the right sibling here? Print plus. What is the right sibling here? Print plus. So we need to print it. We need to print it. Plus completed, T completed, print completed. Now I need to move to the right. That is R. Coming to the R, again, here I am having, so again force. The again left is plus, we don't do anything. So after T is having left and right. Here we need to print 2, sir. Here we need to print 2, sir. After that I need to move to the print. Here print means plus, here print means plus. After printing plus, I need to move to again R. Here R is epsilon. Epsilon is nothing but nothing. So that is the thing. So after completion of the DFS, the evaluated expression is 95 plus 2 plus 95 plus 2 plus, sir. So we'll check is the given thing is in the given answer or not. Yes, 9 plus 5 plus 2, not 1, sir. This is not a, sir. So 9 plus 95 plus 2 plus. So it is there. 952 plus plus. It is not. It is not. So option B is correct one, sir. Option B is correct one, sir. So first of all, we need to construct a parse tree for the given translation scheme or for the given grammar. After that, we need to add the semantic rules. That is nothing but grammar symbols. After adding or after attaching the grammar symbols, we need to perform the DFS. DFS means depth first search from left to right. It clearly mentioned from left to right. So if there is no left child and right child, we can complete it. We can complete it in the same manner. For yes, I came to left. There is a left child. So for that purpose, I came again to left. Here for num, there is no left and right. So then I move to the right sibling. So right sibling is print. So left completed, right completed. That's why after printing 9, I move to the R. Again, here plus and here plus is not doing anything. Then move to the T. T is left having left child as well as right child. Left child is doing nothing and right child is printing 5. So 5 also printed. After that, it is moved to the next right sibling. So the right sibling is print plus. That's why plus is printed. After that, it is moved to the right sibling. That is R. In that R, left is plus. So it is not doing anything. After that, it is moved to the right sibling. That is T. T is having left and right. So in that, it is printing 2. So 2 also printed. After that, it is moved to the print plus. So plus also printed. After that, only epsilon is there. So this is the DFS traversal, sir. This is the way of DFS traversal. I will explain one more question, sir. After that, if you are having regarding doubt or ambiguity, you can ask. So this is the way for evolution of translation scheme. For evolution of translation scheme, sir. This is the way for evolution of translation scheme. Right. We'll see one more, sir. We'll see one more problem. Consider the following translation scheme. Consider the following translation scheme. S derives ER, R derives star E, print star, print star, semicolon, R slash epsilon, and E derives F plus E print plus slash epsilon, sorry, slash f. F derives s id print id dot val. id dot val. Here id is token and id dot value is value, sir, corresponding integer value, and the given input string is 2 star 3 plus 4. 2 star 3 plus 4, sir. So that is the thing. For this, first I need to construct the parse string. Suppose if I start at s, E can produce f plus e or f, but starting I am having 2, after that star is there. If I take e derives f plus e, it gives some plus operator operand after first operand. That's why I am choosing f in place of e. F is deriving s as well as id, but I need the starting value. That's why I am taking id print id dot value, print id dot value, id print id dot value. Here f is also having two options. One is yes, another one is this one, sir. But first of all, before going to take a star, just one value is there. So for that value, for that purpose, I am taking id and f print id dot value, sir. So I can replace after attaching the grammar symbols, I can replace it with 2. Okay, we will see it later. So then here 2 completed. After that I need a star. So here R is producing this one as well as epsilon. So I need this one. That's why I'm taking this one as star E and print star E print star. After that there is one more R. So here if you see, so one value is completed. After that, so star is also there in between these two. Then E can be expanded as F plus E and print plus. F can be expanded as id and id dot value, print id dot value, and E can be expanded as again F, and F can be expanded as id print id dot value, So print id dot value, sir. So I started at S. So from S, E and R. So this production I have taken. After that, E can be replaced with this one, and F can be E can be replaced with F. After F, ID and print value. So according to the given input, we need to expand it, sir. So for that purpose, I have expanded like this, and this is completed. All are completed. And for this R, I am placing epsilon. After that, suppose by giving or by attaching grammar symbols. What is the grammar symbol here? 2. And what is the grammar symbol here? 3. And what is the grammar symbol here? 4. Then we need to do DFS from left to right. DFS from left to right. So I started at root, sir. Then I came to depth words, and then from E to F and F to ID. So for ID, there is no left, there is no right. Then I move to the right sibling of ID, right sibling of ID, because for F left completed, but one more child is there that is not completed. So suppose if it is all completed, then I can move to the right sibling of F. So here left is not completed. So sorry, sir. One more is not completed. That is right of F. So by execute this, 2 will print. By execute this, 2 will print, sir. After printing 2, so left completed, right completed. There is no children for F. So after that, I need to move to the right sibling of F. Is there any right sibling for F? No. So I need to backtrack. Sir, for DFS, there is a backtracking. But for BFS, there is no backtracking. This is the difference between DFS and BFS. So I need to backtrack. For E, there is a right. For E, left everything completed. There is no right. Then I need to move to the R, E right sibling, because E and R came from same parent. So I need to move to the R here. After that, plus. So from plus to E. So from E to again F to again ID and ID value. So that's why it will print 3, sir. After that, plus. From plus to E. From E to F to ID and 4. So that will also print. After that, it is moved to the print plus before print star, because it is left. After completion of left only, we need to move to right, sir. Left to right, we need to perform. That's why plus, after completion of this one, we can backtrack. After backtracking, print star, and that is last one is epsilon. So this is the evaluated output of the given translation scheme. For the given input, 2 star 3 plus 4. 2 star 3 plus 4, sir. So this is the thing for evaluation of translation scheme. For the given input, sir. So this is about the Sdt, sir. Till now we have discussed many things regarding Sdt and semantic analysis. Coming to the today's class, we have discussed mainly L attributes and S type definition attributes. So coming to the S type and L type attributes, S type S attributed definition and L attributed definition. So we have discussed these two things, and we have done problems on how to find the L attribute type and S attribute type problems. After that, we move to the translation scheme. Sorry, translation scheme is also nothing but SDT. But in that SDT, the productions, middle of the productions may have the semantic rules. So that is nothing but a translation scheme. So for the given SDT, we constructed the translation scheme. For the given SDT, we have constructed the translation scheme. Construction of translation scheme for the given SDT. So for if it is a synthesized attribute, we add at the end. Suppose if it is the inherited attribute, we add at the middle. But that should be the proper position. Sir, how can I find the proper position, sir? Before the non-terminal of or before the computed non-terminal of, we need to insert. We need to insert the semantic rule. We need to insert the semantic rule. And next one is how to evaluate. How to evaluate. For evaluation of translation scheme for the given input string, we need to construct the parse tree. After that, we need to attach the semantic rules. Then we need to evaluate it or DFS draw. Then we need to do the DFS travel, sir, from left to right, sir. From left to right. So these are the things, sir, regarding SDT. So now we are moving to the one more new topic. That is nothing but intermediate code generation. Intermediate code generation. So from lexical analysis to, we move to the syntax analysis. Syntax analysis to the semantic analysis. And now from semantic analysis to the intermediate code generation, I am moving. So lexical analysis gives the tokens to the syntax analysis. Syntax analysis constructed the parse tree and given the parse tree to the semantic analysis. Semantic analysis gave the annotated parse tree to the intermediate code generation. Before going to intermediate code generation, if we see the drawbacks of SDT or semantic analysis. SDT or semantic analysis. The main goal of the semantic analysis is construction of annotated parse tree, and along with that, it needs to find the semantic errors. It needs to find the semantic errors. The semantic errors can be divided in two types. One is static semantic errors, and another one is dynamic semantic errors. Dynamic semantic errors. Sir, what are the errors called as static semantic errors, and what kind of semantic errors comes under dynamic semantic errors? For example, using variable without declaring the variable, sometimes we may use, for example, int a comma b is declared, but I am using c is equals to a plus b. I didn't declare c, but I am using c. I didn't declare c, but I am using c. This type of error is called as a semantic error. We can identify those kind of errors. We can identify this kind of errors. So this kind of semantic error can be identified by the semantic analyzer. And next one is coming to multiple declaration of same variable. Multiple declaration of same variable. And third one is incompatible semantic errors. Incompatible semantic errors. Semantic errors are semantic incompatible expressions. So these three comes under static semantic errors. Syntax analyzer can identify or detect this kind of errors. These kind of errors. Or if you see one more error, that is array out of bounds. Array out of bounds. Another one is divided by 0. Divided by 0. These two are also related to the type, not to the structure. Not to the structure. These two are also related to the type. So the type errors are called as semantic errors. The type errors are called as semantic errors. So these type errors are not detected by semantic analyzer. That is the disadvantage. These are not detected by the semantic analyzer. So simply I can say that semantic analyzer cannot detect dynamic semantic errors. Semantic analyzer cannot detect dynamic semantic errors. What are the dynamic semantic errors? Array out of bound error. Another one is divided by 0 error. That's why we can call these errors are runtime errors. Runtime errors. So these can be detected and these can be identified with the help of exception handling. So these are not identified at the compiler time or compile time. At the compilation time, we could not find dynamic errors or dynamic semantic errors. Dynamic semantic errors. That is the disadvantage of the semantic analyzer. That is the disadvantage of the semantic analyzer. And the next concept is ICG, intermediate code generation. Intermediate code generation. Sir, what is the purpose of intermediate code generation? Or one more question is, without intermediate code generation, is it possible to construct the target code or not? Target code, can we construct the target code or not? Without intermediate code generation, can we construct the target code or high level language to low level language? Is it possible or not? Yes, it's possible, sir. Yes, it's possible. But it is without intermediate code generation, without ICG. That is the space complexity is more, plus time complexity also more. By converting it into intermediate code, so that space complexity and the time complexity will be reduced. That's why we are using intermediate code generation. Without using the intermediate code generation also, we can construct the target code, or we can give the target code, but that space complexity and time complexity is more. So for reducing the time complexity and the space complexity, we are using intermediate code generation. Intermediate code generation takes the input as annotated parse tree. This annotated parse tree can be represent different intermediate code formats. For intermediate codes, there are two types of intermediate codes, sir, majorly. There are two types of intermediate codes. They are tree format form of intermediate code and linear form linear form of intermediate code. So there are two types of intermediate codes, sir, majorly. One is tree type form of intermediate code. Another one is linear form of intermediate code. And coming to the tree type, there are two types: syntax tree format. One is syntax tree format. Another one is DAG. Another one is DAG. Sorry, sir. Another one is DAG. 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 So these two comes under tree format of intermediate code. Another two are one is three address code. Three address code. Another one is postfix code. Postfix code. Another one is postfix code. Simply, the intermediate code can be represented in two ways. One is a tree format, another one is a linear format. Coming to the tree format, there are two ways. One is the syntax tree, another one is the DAG representation. DAG is nothing but directed acyclic graph. Directed acyclic graph. We will explain one by one, sir. Tree address code and postfix code. Another one is postfix code. So these are the four different kind of intermediate code representations. So coming to the starting one and first one, syntax tree. Sir, what is a syntax tree? So in the initial classes I mentioned, syntax tree is also called as parse tree. But there is a small difference. The difference is we can call the optimized form of syntax tree is nothing but the optimized format of syntax tree is nothing but the optimized format of parse tree is nothing but syntax tree. Optimized form of parse tree, optimized format of parse tree is known as syntax tree. Syntax tree is nothing but optimized parse tree. Sir, what is an optimization? Optimization means the best format from the given all. What is the best format regarding time and regarding space? So we cannot assess and we cannot define from this definition. For that purpose, I am giving one more definition for this syntax tree. Syntax tree can constructed by remove all non-terminals. Remove all non-terminals from parse tree. That is syntax tree. It is very simple. So optimized format is not optimized format of parse tree is known as syntax tree. And we can also simply what we can say, remove all non-terminals from parse tree. Then the resultant tree is called as syntax tree. So we can construct syntax trees. Note, we can construct syntax trees only for expression statements. Expression statements means the statement which is having operator plus operand. operand. Only operands are there. So then we cannot construct. Then we cannot construct the syntax tree for that cell. Then we cannot construct the syntax tree for that person. So first thing is syntax tree is nothing but optimized format of the parse tree. And simply we can say that by removing all non-terminals from this parse tree, we can get the syntax tree. We can get the syntax tree. For example, S is deriving A equals to E, and E is deriving E plus T, and T and F, and F means F to B, and coming to the T star F, from T to F, F to C, and F to D. So this is the parse tree. This is the parse tree, sir. By removing all non-terminals, I can get the syntax tree. I can get the syntax tree. See, sir, no S here. So no S is there. So there is A. So A is left to equals to. For that purpose, I am doing this one as root, sir, equal to S root. For equal to the right hand side, this is everything is right hand side of equals to. So for that purpose, I move to the right hand side. There is no E, there is no T, only plus is there, sir. So for the plus, E is not there, T is not there, and B is not there, sir. So only B is there, sir. So coming to here, T is not there, and there is a star. And for star left, F is not there, and only C. And for here, after star, F is not there, sir, that is D, sir. This is nothing but syntax tree. That is nothing but syntax tree, sir. That is nothing but syntax tree for the given parse tree. By removing the non-terminals, from the given parse tree, we can call that one as syntax tree. By removing all the non-terminals, we can get the syntax tree. And for syntax tree, some more rules are there, sir. For syntax tree, some more rules are there. They are: syntax tree gives the order of evolution of syntax tree gives the order of evaluation of expression. And third one is order of evolution of expression. And this is the one more statement, sir. And in syntax tree, all operators present at intermediate nodes, and all operands present at leaves or at leaf nodes. Operands are at leaf nodes and operators are at intermediate nodes. And fifth one is in syntax tree. In syntax tree, common subexpression can repeatedly evaluated. So here some properties are there. Syntax tree is nothing but optimized format of the parse tree, and we can remove, or we can also give one more definition, that is nothing but by removing all the non-terminals of the parse tree, we can get the syntax tree. And second point, first, this is the first point. If you take this one as the first point and this is second point, we can, or the syntax tree gives order of the evolution, and the syntax tree constructed only for the expression trees. Syntax tree can be constructed only for the expression statements. Only for expression statements, we can construct syntax tree. We can construct syntax trees. So that is then another rule. And the different rules are. Syntax tree gives the order of the evolution of the expression. How to evaluate the expression can be given by the syntax tree. So it will give. So, and what is the order of the evolution of the expression? And next one is the syntax tree. In a syntax tree, all the operators are intermediate nodes, and all the operands are leaf nodes. All the operands are leaf nodes, and all the operators are intermediate nodes. And simply, finally, the syntax tree, in a syntax tree, common subexpression. So what is common subexpression? For example, a plus b multiplies a plus b. So here a plus b, and here also there is a plus b. A plus b is commonly there, sir. So, or else a minus a plus b. Here, one time, second time, and third time. Common subexpression. So, here we will evaluate a plus b. Here also we will evaluate a plus b. Here also we will evaluate a plus b. Suppose if a value is 5 and b value is 2, so a plus b means 7. Here also a plus b means 7. Here also a plus b means 7. So the common subexpression repeatedly evaluated in syntax tree. So this is the drawback of the syntax tree. So for every expression, the common expressions are repeatedly evaluated, even though there is no necessity. Suppose if you get the answer here, you can use that one here and in this place, but every time it is evaluating. That is the memory wastage is also there for that purpose, because it will get some result, get some result. And one more thing is time is also waste. So our time complexity is also more. For that purpose, that is the complexity of the, or that is the difficulty, or that is the disadvantage, or that is the drawback of the syntax tree. Syntax tree is the one of the format of the intermediate code format. So that is having some rules. By removing all the non-terminals, we will get the semantic tree. Semantic tree can be constructed only for the expression trees. Coming to the syntax tree, all the leaf nodes are called as operands, and all the intermediate nodes are called as operators. And it gives the order of the evolution of an expression. It will give the order of the evolution of the expression. And if we see some examples regarding syntax tree, so you may get the questions from syntax tree like this. So construct construct syntax tree for the following expression for the following expression. So the given expression is x equals to b star c plus b star c, and b star c. For this we need to construct the syntax tree, sir. For this we need to construct the syntax tree. So for the given rules, in the given rules we are having one point, that is syntax tree gives the order of evolution. So order of evolution, first we need to check what is the order of the evolution. So star operator is there, plus operator is there, sir. What operation we need to do first? Star operator. So multiplication operator will do first. So it is left associative. That's why left to right associative. That's why this is first one and this is second one. This is first one and this is second one. After that, we need to add these two. That's why this is third. After completion of this one, we need to assign the result to the x, and that is the fourth one, sir. If we see first one, b star c, and next one is b star c. From this I can write star c. So I can eliminate the star here. So b star c. I will get the result here. I will get the result here as b star c. B star c result I will get here. So in the same manner, here also after that, the same manner. Star c. So it is also gives the same b star c, sir. From these two, this value and this value, I need to add. This value and this value I need to add. After that, b star c plus b star c. That value will gives here. That value will be evaluated here. After that, that value needs to be assigned. To x. So this is the syntax tree for the given expression. What we need to do is we need to check what is the order of evolution. Based on that order, we need to construct the parse tree. First, here we need to calculate b into c. Here also b into c. So this is the first step and this is the second step. After that, we need to perform addition operation. After that, we need to assign the result to the x. After that, we need to assign the result to the x. So that is the thing. Sir. So this is the syntax tree construction for the given expression. Syntax tree construction for the given expression. So one more gate question is there, sir. After completion of this gate question, I will close the session, today's session, sir. We'll see one example which is previously asked question, sir. Which is previously gate asked question. Consider two binary operators. Two binary operators with the precedence of operator being lower than that of the operator this one. Operator is right associative, while operator is left associative. Which of the following represents the parse tree for expression 7, 3, 4, 3, 2. So this is the input given, sir. This is the input given. This is the expression. Simply he is asking what is the syntax tree or what is the parse tree. What is the syntax tree or what is the parse tree for the given expression. With the given properties. The given properties are precedency is given and associativity is also given. Precedency is given and the associativity also given. The options are option B, option C, option D, none, sir. Option D, none. So this is the question previously asked regarding intermediate code generation and syntax tree. In the given question, so the expression is 7 down arrow, 3 up arrow, 4 up arrow, 3 down arrow, 2. So this is the given expression, sir. And up arrow having highest precedency, then down arrow, it is lowest precedency. And it is left to right associative. And this is right to left associative. Or else right associative, left associative, simply we can say that. So this is the thing. So simply we know that in the order of the evaluation, the operator which is having highest precedency will evaluated first. The operator which is having highest precedency will evaluated first. So that is the thing, sir. So for that purpose, what is the operator having highest precedence? Coming to here upward direction or upward arrow having highest precedence. So for that purpose, first we need to evaluate these two. In these two, what we need to evaluate it first? We need to evaluate it first right, because it is right to left or right associative. Simply right associative. For that purpose, I am taking 4, 3, 4, 3. So this result, with this result, I can operate with this one. With this result, I can operate the same thing with this one. So for that purpose, the result is came. So with that, I need to perform again up arrow, and now coming to down arrow. So that is left to right or left associative. So for that purpose, first I need to perform. So 7. First I need to perform 7. After that, I need to perform. 2. After that, I need to perform 2, sir. So this is the thing. So coming to this one. So down arrow and up arrow. And simply with by seeing the example also, we can reject some answers. Sir, how can you reject, sir? How can you eliminate, sir? Sir, it is having down arrow having less priority, but we are performing first. So this is not correct, sir. So, and here after performing down, we are performing up arrow, but down arrow having less priority than up arrow. So in that category also, we can eliminate these two and we can answer this one, or simply by writing the syntax tree by using evolution order also we can answer the question, sir. Very, very simple, sir. The construction of syntax tree is very simple, and the checking the syntax tree for the given expression is also very, very simple, sir. Very, very simple, sir. So this is the way to construct the syntax tree for the given expression, as well as evolution of the syntax tree or construction of syntax tree for the given expression, as well as removing the non-terminals for constructing the syntax tree. So these are the things, sir. In the next class, I will explain you what is a DAG, how it is different from syntax tree. What are the disadvantages with syntax tree? In the syntax tree, the common sub-expressions are evaluated repeatedly. That is the disadvantage of syntax tree. So, and how can we eliminate that drawback is by using tag or directed acyclic graph. I will explain in the next class, sir. So 3 address code is also very, very important. So you will get the questions on DAG as well as the 3 address code. So these two are very, very important from the intermediate code generation. So in the next class, I will explain you the DAG, how to construct the DAG, or how to evaluate the DAG, and how to construct the 3 address code for the given annotated parse tree. I will explain in the next class, sir. Okay. Thank you, sir. I am closing this session. So if you are having any doubts, I will clarify in the next class. You please ask. Thank you.